My name is Darrell Barnes. Welcome to this basic chemistry throwdown. Remember to do what your teacher wants you to do in your class. For my classes, I want you to highlight. And I want you to study the highlighted material. And that is important because that way we all study the same thing for the test. It's not what's in this video. It's not something I said. It's not something that's in the lab book. It's just what's in your book. And that way we all study the same thing. This is just meant to hopefully give you a little bit of clarity as we go along. What I want to do here is talk about and show you chemically how that the structure of a chemical determines its function. And so within these few minutes, I want to talk about different kinds of bonding. I want to talk about ionic covalent bonding. I want to talk about polar, non-polar bonding as well. And then I want to relate this in the end to pH. And so that's kind of where I'm going for the next few minutes. I'm glad you're here. Keep coming back. Remember to subscribe, like, comment, and share. This is what creates a community on YouTube. Let's talk about carbon. And let's talk about hydrogen. Let's talk about these two. Let's talk about these two chemicals for a minute. On the periodic chart, these numbers tell us things. This number is called the atomic number. And it tells you how many protons are present in this element. The bottom number is called the mass number. And it tells you how many protons plus neutrons. And we'll talk more about this later, and we'll come back and pick up the word isotope later too. That fits nicely with this topic as well. So that if I say that there are 6 protons in carbon, then how many electrons does carbon have?
6.
There are the same. It's the same number. It's neutral. It makes things neutral. There is a way to draw a carbon atom, and if we drew the nucleus of a carbon atom, we would say that there are 6 protons, and we would take this big number and subtract the little number. 12 minus 6 is what? 6. That tells us that carbon has 6 neutrons. Now in chemistry, there are 2 happy numbers. 2 and 8 are happy numbers, and I'm going to be talking about those as we go along. If there are 6 protons, then how many electrons are there? 6 protons, 6 positives. That means there are how many negatives? 6. The same, right? And remember, there are 2 happy numbers, 2 and 8. So basically what happens is the electrons that travel around this sun-looking thing like planets, there are 2 of them in the first level. Why? Because 2 is the first happy number. When we look at the next level, if we place 2 electrons and there are 4 more, then we put those as far apart as we possibly can. So we place these kind of like this. So in its outer shell, which by the way is called the valence shell, carbon is not really happy because it doesn't have 8. It doesn't have a stable octet. It doesn't have a stable valence shell. So here is where we get hydrogen in the mix. Hydrogen has 1 proton. How do I know that? I'll look at this number. How many neutrons does it have? 1 minus 1 makes what?
0.
No neutrons in a hydrogen. And if it has 1 proton, how many electrons is it going to have? 1. Okay, so watch how this works. This electron is shared. And so basically, by this hydrogen sharing this electron with carbon, it's happy because it has the happy number of what? 2. Okay? Now watch what happens all the way around this. We have another hydrogen right here that shares an electron. We have another one here that shares an electron. And we have another one here that shares an electron. And so basically what happens is when carbon shares with 4 different hydrogens, Look at the outer shell of carbon. 2, 4. How many electrons does carbon now have access to? It has 8, and that is the second happy number. So this is a happy structure. If we draw the structural formula, we draw like this. We say that methane or bowel gas is CH4. And basically each little dash is a single bond, and it represents how many electrons being shared. How many electrons are shared here? 2, 4, 6, 8. Each bond represents 2 electrons being shared. So if it was a double bond, it would be 2 times 2 makes what? 2 times 2 makes 4. Okay, lovely. So I told you I wanted you to see how that the structure of a chemical determines its function. That's kind of what I'm going to get to next. If we took this atom and we drew it in a 3-dimensional structure, then basically there would be a hydrogen going straight up, a hydrogen going kind of out to the front, and then there would be one kind of moving out back. So that if we drew it, it would form kind of a tetrahedral structure, kind of like the structure of a pyramid, kind of something like this. There would be a hydrogen out back, so that if you picked up this molecule, it wouldn't matter how you turned it, it would look about the same, roughly the same. I probably didn't draw that perfect. Someone else could do a better job than me on that. But when there is, listen close, this is important. When there is a molecule that it doesn't really matter how you turn it, it kind of looks the same no matter how much you turn it. That basically is a non-polar compound, and it's not going to jive with water. Water is not going to dig it. Have you ever made some dressing, put some oil and vinegar, and you can get bossy with it and shake the heck out of it to mix it all up, but the minute you set it down, what starts happening? The oil starts going back to the top, because oil is, this by the way is like a hydrocarbon. It's got hydrogens and carbon in it. It doesn't mix with water. And I'm going to show you next why it doesn't. This would be called non-polar covalent. Why is it non-polar? Because it looks kind of the same all the way around the molecule. Why is it covalent? Because there are electrons being shared. Let's add another player into the mix here. Let's put oxygen into the mix and see if we can kind of squeeze this onto the board. Oxygen is not going to work. Let's go with a different color. Oxygen has 8 protons and a total of 16 electrons. A total of 16 protons plus neutrons. It'll have 8 electrons as well. If we do a model for oxygen, check this out. How many protons would I put in the nucleus for oxygen, class? How many would I put? 8, okay. And 16 minus 8 makes how many neutrons? 8 neutrons, okay. Remember that the first shell will hold up to 2 electrons, and if I place 2 and I have a total of 8, how many more do I have left to go? 6 more to go. Okay, watch this closely. 1, excuse me, there's a problem here. I need a new orbit. Okay, 1, 2, 3, 4, 5, and 6. And so what I want you to notice, and I'm getting everything very jumbled up, is that this is oxygen. And if we add in a hydrogen, there's 1 proton and there are no neutrons in hydrogen. And if we share an electron here, and then if we do the same thing here, 1 proton, no neutrons. If we share an electron here, look at what we have. 2, 4, 6, 8. We have a happy compound. And what do you call it when you have 2 hydrogens and 1 water? What do you call it when you have 2 hydrogens and 1 oxygen? Yes, I just told you the answer. H2O is a high quality substance made from 2 hydrogens and 1 oxygen. Now, here's where I want, again, to talk about how the structure determines the function. This is really important, what I'm about to talk about. Because there are lots of electrons clumped over here, this end is roughly electronegative, and because this end is electron poor, this is electropositive, and so is this right here. So that if I drew a little kind of a stylized version of this water, it would be negative on this end and positive here, and we have 2 electrons shared here. Notice that there are 2 unpaired sets over here and here. By the way, water also forms this tetrahedral form, and that's why it's bent like this. That's why we bend it like that, because there's some unpaired electrons that kind of force those hydrogens into a bent configuration. Now, what's so neat about water is that when you mix it with other water molecules, it flip-flops like this. The negatives and positives are attracted to each other, so that the positive hydrogens are attracted to the negative oxygens. And so basically, water is attracted to itself. And it basically makes water cohesive. It wants to stay together. And I think what we will do in this video, instead of talking about ionic, because I'm running out of board, we're going to just relate this idea to pH, because this is the perfect time to do it. So we'll do that, and then we'll erase, and we'll do another video on ionic bonding next. Water, in a strange way, if you have water, you mostly have water. Hello. But it's possible when you have water, it is mostly water. But in a small way, it will dissociate to form hydrogen ions, and it will dissociate to form hydroxide ions. I cannot seem to get everything separate. Hydrogen and hydroxide ions. If there are lots of hydrogen ions, then there is a low pH. And if there are lots of hydroxide ions, then you have a high pH. What is that called? It's not acid, it is a base or alkaline. Okay? So let's relate this just a little bit for just a couple of minutes to a pH scale. Let's talk about this for just a minute. In water, if the hydrogen ions equal to the hydroxide ions, then you have a specific case of pH called what? What is pH 7 called? That's called neutral, okay? But what if you have a lot, let's say that you have a lot of hydrogen ions. Let's say that you have lots of hydrogen. It's not very intuitive to think that the more of something you have, the lower the number it is, but that's how it works. And the pH is equal to the negative log of the hydrogen ion concentration in moles per liter. And because it's got this mathematical relationship, there's an inverse relationship with the numeric ordering of it. Let's say that lemon juice is about a pH of 2. And let's say that coffee is about a pH of 5. Let's say that. Well, an interesting thing to notice is that between every number on the pH scale, there is a tenfold difference. Tenfold. So basically we would say that coffee is 10 times 10 times 10 amount weaker than lemon juice when we talk about acid. So what's 10 times 10? 100. What's 10 times 100? 1,000. So we would say that coffee's 1,000 times weaker. If this is correct, I think it is correct. There are some other molecules that you might recognize. Ammonia is found in a lot of cleaners. It's probably got a pH of 11 or 12. Milk of magnesia is another one. Remember this. Here's something that's really important for you and I to remember. What makes this dangerous for us is how far is it from 7? So the truth is, an acid battery can burn skin, and so can an alkaline battery. Either one can. And somehow we seem to habitate pretty nicely with things kind of on the middle part of this chart. So let's review just for a moment. One of the things that I wanted you to find, by the way, water is called polar covalent. Polar covalent. Okay. What I wanted you to see in this video is that the structure of a chemical compound determines how it acts. Like, for instance, the very fact that the carbons and the hydrogens are equally distributed makes this compound not want to interact with compounds like water, which are polar covalent. There's one clearly positive end and one negative end. Water tends to be attracted to itself. It's cohesive. It can actually kind of act as an adhesive. One last thing that I would like to add in, which is kind of important, and this will lead us into the next video that we'll do talking about ionic compounds. But if you had a compound like sodium chloride, for instance, sodium is positive and chlorine is negative. And so if you put salt in water, then the hydrogen ions would help pick that chlorine apart, and the sodium ions would be attracted to the oxygen, or the oxygen will be attracted to the sodium, and that is what causes compounds to dissolve in a liquid environment. We call water the universal solvent, and we call things that dissolve in the solvent, we call those solutes. So keep coming back, come back to the next video, because we're going to talk about ionic bonding, which is basically giving and taking. That's kind of interesting as well, because we have covalent compounds in our body, fats and things like that. We have water as a transporter of chemicals, and then ionic compounds are things that are like sodium chloride that I just talked about. So we'll talk about that next. For just a minute, let's talk about isotopes. Isotopes are different flavors of chemicals. And if we looked at carbon, for instance, carbon 12 has 6 protons. Remember, this bottom number is the proton plus the neutron number. So 12 minus 6 makes what?
6.
It makes 6 neutrons. So carbon 12 has 6 neutrons. What about carbon 14? 14 minus 6 makes what? 8 neutrons. So it's possible to have an element that has a different number of neutrons, but it's the same element. Why is that important? Because it's the proton number that determines the element's identity. And in medicine, or actually in science, we think about carbon 14 as an isotope that's taken up by critters that are in the sunshine, and it helps us roughly date how old these things are by how much of this isotope is left within the tissue. That is what makes carbon 14 important.